Hello, everyone. If you've been in medicine for a while, you've probably heard of someone talk about the ST segment being elevated or depressed. So, a quick question. When you say a certain part of the EKG is elevated or depressed, it's elevated or depressed related to which part of the EKG? Go ahead and pause the video and think about an answer. In the prior session, we've talked about the different waves in an EKG, and when it's printed on a piece of paper, it would be awesome if there were an easy way for us to look at how long the duration of a wave was, how the shape of the wave changed over time, and also how strong a specific wave was. So, to help us with this, we have the EKG paper that you can see in the background. So, in essence, the EKG paper is made up of several large squares. And as you can see, each of the large squares is divided into 5 small squares. Now, a specific convention that's followed is that the paper usually runs at 2.5 centimeters per second. And as you can see, each of the small squares is 1 millimeter long and 1 millimeter tall, and each of the large squares has 5 smaller squares. So each of the larger squares is 5 mm long and 5 mm tall. So if you have 2.5 centimeters going through the machine per second with a print of whatever is happening in the heart, it translates into 5 large squares are being printed upon every 1 second. It also means that one large square would be equal to zero point 0.2 seconds. How did we get that? It's 1 by 5, which is 0.2, and one small square would be equal to 0.2 by 5 because each large square has 5 small squares, and that would be 0.04 seconds. So if you're looking at the frequency of a wave, meaning you're trying to figure out how frequently a specific wave is occurring, you could measure the distance between any two waves and use this information to figure out the frequency. So for instance, let's say there is one large square between each wave. You would know that the frequency would be equal to number of waves by the time. So we said that there's one wave after each large square. So the time elapsed from here would be one large square that's equal to 1 by 0.2 seconds. So that would be equal to 5 waves per second. And that would be equal to 300 waves per minute. If there were two large squares between each wave, then the frequency when there are two large squares would be equal to one wave per two large squares. That's equal to one wave every 0.4 seconds, and that would be 2.5 waves per second, and that would be equal to 150 waves per minute. So in essence, if you think through the process, you could pretty much estimate the frequency of a wave by simply dividing 300 by the number of large squares between the waves. So number of large squares. And because we said that each large square has 5 smaller squares, if you were to count the smaller squares, you would end up with 300 by number of small squares divided by 5, because the number of small squares divided by 5 equals the number of large squares, or put another way, this would be equal to 1500 by number of small squares. Also, if you had to estimate the duration of a certain wave, let's say a wave goes like so, You can easily estimate the duration by counting the number of large squares and multiplying that by zero point 0.2 seconds. So in this case, it's going to be 2 large squares times zero point 0.2 equals 0.4 seconds. Another option would be counting the number of small squares. So in this case, there are 10 small squares. And as we know from earlier, each small square is 0.04 seconds. So you multiply that with 10 and you end up with the same zero point 0.4 seconds. So this way, by looking at the paper and understanding how the convention works, you can easily estimate the duration of a wave, and you can also estimate the frequency of a wave. Now, because the paper keeps moving at any given point, if there is a change in the nature of the wave, it's easily captured. So because the paper is moving, if you see a wave that looks like so, it means that the initial wave of depolarization was moving towards the specific lead, and then it was moving away from the specific lead. The last convention to understand prior to delving into how to read an EKG would be to know that the height, so each 1 millimeter of height corresponds to 1 millivolt in amplitude. So the taller a wave is, the more intense it is. Now, before trying to read an EKG, make sure that we know the machine's properly calibrated. The way you would do it is by looking at this what looks like two lines that are perpendicular to each other. The vertical line must be calibrated so it's 1 centimeter. So it should be 2 large boxes tall or 10 small boxes tall. And in essence, if that's done, it means that the machine's calibrated so every 1 millimeter is equal to 1 millivolt. On the other hand, the horizontal section tells us how fast the paper is moving, and as long as it has one large box, it means that it's calibrated to run at 2.5 centimeters per second. The last convention is that typically an EKG is printed on a strip that's about 10 seconds long. So the whole duration of this is about 10 seconds. So just to reiterate what we've discussed, the EKG strip runs at 2.5 centimeters per second. You can estimate the frequency of a wave by dividing 300 with the number of large squares or 1500 with the number of small squares, and that would give you the frequency per minute. You can see how a wave changes over time, and you can also measure the intensity of the wave, and each 1 millimeter change in the height of the wave would mean that the amplitude has changed by 1 millivolt. Now, in terms of reading an EKG, there are 4 basic steps, and when you're trying to read an EKG, always make sure you're doing these 4 steps in every single EKG you read. That way, you would minimize the chance of missing something that is not so obvious. Also, if you can master the art of knowing which EKG is normal, figuring out the abnormal parts would help you reach the ultimate diagnosis. So, in essence, what you want to do is go through the 4 steps, look at which parts of the EKG are normal and what the deviations are, think through all the abnormalities, and come up with the diagnoses that would explain all the abnormalities you're seeing. Using the information we've learned, let's try and estimate the frequency of QRS complexes in this EKG. So we have one QRS complex there, one there, one there, one there, and so on and so forth. And notice how they're pretty much all happening fairly regularly. So if you had to estimate the frequency of the QRS complexes, we can see that there are approximately 3 to 4 large boxes between each of the complex. So the rate would be equal to a range between 300 divided by 4 to 300 divided by 3. So the heart rate in this case is between 75 and 100. Another way to estimate it would be based on the number of small squares. So if you would count the number of small squares between consecutive waves, we can probably assume that there are about 17 small squares. 1500 divided by 17, and that would be approximately 88 beats per minute. Now, at times you would see that the interval changes between each wave, and so another way to estimate the heart rate would be counting the total number of complexes on a given EKG strip. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you have 13 beats, and we said that each strip is typically 25 centimeters long or about 10 seconds long. So if you had to estimate the number in a minute, you would multiply it by 6, and so you would have 78 beats per minute. All right, and that's how you would measure the frequency or the rate of the QRS complexes, and you could do that for the P waves as well. So the first step to reading an EKG is always to start with the rate. And if it's regular, you could use one of these two methods. So you either divide 300 by the number of large squares between each wave, or 1500 by the number of small squares between each wave. Or alternatively, you can simply count the number of waves on a given strip. So pretty much count all the number of waves and multiply that by 6 to get the frequency. Now, the next part to reading an EKG would be understanding what the rhythm of the EKG is. So as we talked about, typically conduction starts with the SA node and the atria are first to be depolarized, and that would cause the P wave. And following that, the impulse goes through the AV node and eventually reaches the ventricle, where the depolarization of the ventricle causes the QRS complex. So for a rhythm to be considered sinus, which is normal, you would look for the following characteristics. The first thing you would want to look at would be to look at lead 2 and see if all the P waves look upright and if all the P waves are symmetrical, and if the PR segment is approximately of the same duration in all the beats. The second thing you'd want to look at is to see if the P waves occur at regular intervals. And just eyeballing the EKG, they are occurring at fairly regular intervals. And the third thing you'd want to ensure is to see if each P wave is followed by a QRS complex. So here we can see that each P wave is followed by a QRS, and so on and so forth. So if you see this happen, the EKG shows that it's normal sinus rhythm as long as the heart rate is normal. And the normal heart rate, so the normal heart rate equals 60 to 100. So as long as you've seen that the heart rate is between 60 and 100, and the rhythm is sinus rhythm, you can say that the EKG is revealing normal sinus rhythm. The next thing you'd want to observe is the axis. So the first thing to look at would be the axis of the P wave. So notice how the P waves are upright in lead 2 and inverted in AVR. So normally you would want P wave in lead 2 to be upright and AVR to be inverted. The next thing you'd want to look at is the QRS complex. And as we've talked about previously, you would want to look at leads 1, 2, and AVF, and look at whether the wave is predominantly positive or negative. In this case, you can notice that the R wave is bigger than the S wave, so the R is bigger than the S. Again, you can notice that here it's predominantly positive, and AVF is also predominantly positive. So if we draw out our leads, we have lead 1, AVF, and lead 2. So 1, 2, AVF. We have our imaginary line perpendicular to lead 2, and we said that 1 is positive, so the axis is somewhere here. We also said 2 is positive, so the axis is somewhere here. And we said AVF is positive, so the axis is somewhere here. So the area of overlap in this specific scenario is right here. So in this person, the axis is QRS axis is between 0 and 90 degrees, and this would be normal. So we've started with the rate, then we've looked at the rhythm, and then we've looked at the axis. Once we've done this, you would want to make sure that the intervals and morphology of the waves are okay. So let's start off with the P waves. The P waves are best seen in lead 2. So P waves are usually best evaluated in lead 2. And as we talked about previously, they're upright in lead 2, inverted in ABR, and often biphasic in V1. The axis is usually between 0 and 75 degrees, and usually they're not too wide and not too tall. So usually they're less than 0.12 seconds wide, and the amplitude is typically less than 2.5 millimeters. And also in V1, where they're biphasic, the amplitude of the positive wave is less than 1.5 millimeters, and the negative wave is typically less than one small box deep and one small box wide. So if it's more than one small box deep or more than one small box wide, that could be abnormal. The next thing you would want to look at is the PR interval. So the PR interval, as you may remember, is from the beginning of the P wave to the beginning of the QRS complex, and this is usually between 0.12 to zero point 0.2 seconds. So in essence, that's between 3 and 5 small boxes. And because not much is happening in the heart, typically the PR segment should be flat and at baseline. Now, when we're talking about baseline, the baseline of an EKG is determined by looking at the TP segment. So it's the segment between the end of T wave and the beginning of P wave. So in this person, this would be considered the baseline. So notice all the TP segments, that's what gives you the baseline. And when you say the other waves are elevated or depressed, it's relative to the TP segment. The next thing that you would want to look at is the QRS complex. And usually the QRS complex is less than zero point 0.1 seconds in duration. So usually the number of small boxes that contain the QRS should be less than 2.5. The normal axis would be between negative 30 and positive 90. So that's the normal QRS axis. And you shouldn't really see any Q waves that are too deep or too wide, especially in contiguous leads. What are contiguous leads? Think of leads that are next to each other. So leads 1 and AVL would be contiguous. Leads 2, 3, and AVF are all looking at the inferior wall and would be contiguous. Leads V1, V2 would be contiguous. V3, V4 would be contiguous. V4, V5 would be contiguous because they're placed next to each other, even though one is an anteroapical lead and the other is a lateral lead. V5, V6 would be contiguous. So essentially, leads that are next to each other are contiguous leads. Notice how the R wave is not very tall, but the S wave is pretty deep in V1. This makes sense, right? Because V1 is placed in the front of your chest and the left ventricle is to the left of your chest, and that's the bulkier part. So you would expect the wave to be more intense when it's traveling away from the lead. But notice how as you go laterally, the R wave is progressively getting taller, and eventually in this EKG by V3, the R is bigger than S. So usually the R wave should be bigger than S wave by V3 or V4. If this is not the case, if the R wave is bigger than S wave prior to V3, that would be considered early progression of the R wave. And if it's happening after V4, that would be considered poor R wave progression. The next thing you would want to look at would be the ST segment. So that's the area between the end of the QRS complex and the beginning of the T wave. And notice how it's typically at the level of TP segment. So you would not want to see too much of an ST elevation or an ST depression. And following the ST segment are the T waves. So that's a T wave, that's a T wave, that's a T wave. And notice how the direction of the T wave is similar to the direction of the QRS complex. For instance, in AVL, where the QRS complex is predominantly negative, notice that the T wave is flat and sometimes it can be slightly inverted. So typically, the direction of the T wave is in the direction of the QRS complex. Now, sometimes, aside from the waves we've discussed, you may see a small wave after the T wave, and that would be the U wave. We would also want to look at the QT interval. The QT interval is measured from the beginning of the QRS complex to the end of the T wave in the leads. So that would be the QT interval. And typically, this should be between 0.35 and 0.46 seconds. But the concern with this direct number is that when the heart rate is high, the QT interval decreases, and when the heart rate is low, the QT interval increases. So, to account for the heart rate, we calculate something called the QTC, and the QTC would be equal to the QT interval divided by the square root of the RR interval. So you pretty much measure the QT interval and you divide it by the square root of the RR interval. If you have a calculator, this is easy, but often you look at EKGs on the go. So a good way to ballpark this would be to ensure that the QT interval is less than half of the RR interval, and that seems to be the case in this EKG. At this point, understand that evaluating whether the QT interval is normal or not in a person with bradycardia or high heart rates can often be challenging. So, whenever you're evaluating an EKG, start by making sure the EKG is properly calibrated and you've verified the patient's information. Following this, evaluate the rate of the EKG, then the rhythm of the EKG, then the axis of the P and QRS complexes, and then look at the morphology of each wave as well as the duration and morphology of every segment and interval. Doing so consistently would give you a good grasp of what a normal EKG is, help you understand the variance of a normal EKG, and if you can pinpoint every single abnormality that you see on an EKG, that's a very good first step in terms of interpreting EKGs. Once you know all the abnormalities, it's pretty much a matter of coming with the list of diagnoses that would best explain the abnormalities you're seeing. At this point, I would like to thank Life in the Fast Lane for allowing me to use the EKGs on their site. It's an awesome website if you're interested in learning more about EKGs, and I would strongly encourage you to visit them. Thank you for watching.